All right. So, hello everyone. My name is Viraj, and today we are going to be discussing starters. I think this is starters 135, if I'm not wrong. Yeah, starters 135 discussion for the post-contest discussion for starter 135. And we'll be discussing the ideas and the codes for the first three problems. And for the fourth problem, I'll be going over the idea. All right. And I'll be definitely pasting up a solution in the description of this video. But then again, once the idea is clear, the sub problems is kind of a standard problem that is out there on the internet. So you guys as beginners can take it as a small up solving part, which you can do on your own to understand how did we come up with that idea. All right. All right. So let us start with the first problem. Invert and equalize. Now, this was a pretty straightforward problem, right? Like you were given a binary string in this, s of length n, and you can perform the following operation on it. So it's given that you will choose a continuous string such that all of its characters are equal, and then you will invert that whole substring. So if let's say they are all 0, change them to 1 and vice versa, right? So you need a continuous substring. That's important, right? So if I'm talking about, let's say I'm talking about in this part, I'm talking about, let's say this string, then this is not this is a continuous substring, but then I know that all the characters are not equal. It's 1, 1, 0. Yep. So is this recording available in the TLE? No, it's directly available on YouTube. All right. All right. So coming back, if let's say I have this substring 1, 1, 1, 1. Now this is a continuous substring. Obviously, substring has to be continuous, and everything in this is same. It's all ones, or either it could have been all zeros. If it's all ones or it's all zeros, I can reverse the characters inside this substring. So 1 becomes 0 and 0 becomes 1. So this is what they've done. Let's say the example is 1, 0, 1, 1, 1, 1, 0, 0, 0. And you choose this blue part. That's the 1, 1, 1, 1 continuous substring. You can reverse everything out to 0, 0, 0, 0. Now, the target is find the minimum number of operations needed to make all characters of S equal. Now, pretty straightforward what they're asking you to do. Now, if let's say I have the string, I have the whole string given to me of the n size, then I obviously want that this whole string either becomes all zeros or it becomes all ones. Is this what I want? Yes. Now, out of these two, I want that what I can do is I can say, if I smartly calculate the least number of operations it takes me to convert the whole string to all zeros, let me call that as OP1. And let me say that I somehow figure out the best possible number of operations to make the whole string ones. Let me call this as OP2. Then tell me which out of these two will you take? Like if you have OP1, the best number operations possible for 0 and best number of operations for 1, then it makes sense for me to take the minimum of these two. Yes, OP1 and OP2. That is what is very clear. If I'm able to smartly calculate OP1 and smartly calculate OP2, then the minimum of these two should be my answer. Because arguably, whatever is the minimum would denote that I have converted either all zeros or either in all ones. All right. Now, now, if I want to calculate answers OP1 and OP2, let me try to analyze them individually. So let's say I want to calculate OP1. That means everything should become 0. Now, because everything should become 0, it can happen that initially everything is not 0. Means you will have maybe some zeros, then maybe some ones, then maybe some zeros, then maybe some ones, then maybe some 0, then maybe some 1, and so on. Let's assume this is the string. And you want something that looks like this, all zeros. So it can be very easily seen that the minimum number of operations I should actually do to convert this to every 0 is, let me take up this segment of 1, this segment of 1, this segment of 1, and let me perform individual operations. So I'll say one operation on this segment, everything becomes 0. One operation in this segment, everything becomes 0. One operation in this segment and everything becomes 0. So the total operation count is 3. Can I go below this if I want to convert the whole string to all zeros? No, right? So that is the minimum and the best greedy way of performing the operations so that I convert all the ones to zeros, or exactly all the segments to zeros. So this eventually, this 3 number, what is this denoting? This 3 number is denoting that how many segments of the type continuous type 1 fell in your answer. So if let's say in this case, we were easily able to see that 3 segments were there which had continuous ones. And now if I do the same for zeros, then you will argue that we had 4 segments which had the 0 coming together in a continuous segment. So out of these 2 numbers, that is 3 and 4, it would obviously make sense for me that currently I showed you the case for making the whole string 0, 0, 0. But then what if I wanted to make the whole string 1, 1, 1? Then I would have done the vice versa case. Yes, I would have targeted these green blocks that are all zeros, and I would have converted them to 1. And it would have taken me 4 operations. So that means if I'm somehow able to calculate the segment count of continuous ones, let's call this some value, and the segment counts of continuous zeros, this is the other value. Minimum of these 2 is the answer. Do we now agree to this part? Is everything clear up till here? Yes, this is my approach and got 0. All right, that's great, Anshuman. That's great. Great. All right, so I think this was the 3rd problem in Div4 or 4th problem. I don't know exactly. Like, I'm not sure. 3rd. All right, cool. So is everything clear up till here? Like, is the whole structure clear up till here? Yes, I think it should be. Like, it's not a tough thing to now understand that these are the segment parts. Yes. So now how do I actually calculate this out? Now this is like an implementation problem now. Once we have understood what is the idea was calculate the number of segments of zeros and ones, and I will count them together. So I'll call this as some segment as, let's say, C1. This is the segments of ones coming together, and I'll call this as C0. Then whatever is the minimum, I can print that as my answer. So now from here, the problem is all about implementation. How do you calculate this segment part? All right. So how do you do this? How do you do this? What I have done is like what my approach has been that I can, let's say, like in this case only, I'll have a pointer. I'll run this with the red part. So I'll go to the first index and I'll say first index, if it's a 0, if it's a 1, I'll increment my C1 or C0 likewise. So in this case, because it's a 0, C0, initially everything starts with 0, but now this becomes 1 because I know one segment of 0 is definitely going to be there. Now I will start my actual iteration from this part. This I equals to 1. Or you can say this is my I. All right. Now I'll say that if I index and I minus 1 index, they are not equal, then what does this mean? That means that you have changed into a segment. Is that correct? Let's say you're standing at I and the I minus 1 index is not same as this current index. In this case, it's same. So I know I can move forward. I know that continuously the one segment is getting followed and they are having the same number coming in it. That's 0. But let's say I'm standing over here. This is I and this is I minus 1. I now know that ith index and I minus 1th index characters don't match. That means there has been a transition to a new segment. So if there has been a transition to a new segment, that means something needs to be done. And that something is actually saying that now if there's a transition, up till I minus 1, I was tracking because I had started off with the 0th index being already tracked and then started off with the first index. So I know I minus 1 index up till here, I was already tracking the part. So what I can do is at this current ith index, I can simply ask myself, is there a 1 or is there a 0? If there's a 1, that means a new 1 segment has started. Or if there is a 0, vice versa, there has a new 0 segment started. Do we all get this idea? Yes. So I can now, in this case, I can very clearly observe that a new segment of 1 started. So I'll say C1 becomes 1. And then I'll move my 2 pointers forward. So this becomes I minus 1. This is I minus 1 now. And this is I. Check again. They are equal. Not a big deal. Move on. This is I minus 1. This is I. Different. Now, because they're different, I need to check the I part. I is a 0. That means a segment switch has definitely been done. But the segment switch is now going to a segment that has zeros in it. So I'll increment my C0 to 1 from 2. And so on, so on. This gets followed. And at the end, you will find that you have you have 3 and 4 in this. And I mean, we can look at the code part to understand what more am I doing in this. But then roughly this is the idea. Now, again, implementation is not a big part of this problem. Reason being that you can implement this out in any sort of a method. Like maybe you can take indexes to calculate the difference between that. Maybe you take different 2 pointers. Maybe you don't go with I-1 or I approach. Maybe you go with I and I+1 approach, something like that. It can be done in any order. Yes, do you all agree? The idea should be clear. Eventually, you are definitely calculating the number of 0 segments and number of 1 segments. I was not able to clean up the code. I'll just try to clean up the code right over here only as I go, because it's not a big part. All right. So you guys cannot look at whatever other boilerplate stuff is there, because then again, that's simply running the macros part. But then base structure looks somewhat like this. Yes, I mean it's going to match with you guys also. So what I'll say is, I have taken an input of n. Now I've taken the input of string s. Then c1, c0 starts with 0, 0, as I explained. Now I've taken a very base case, simply saying that if n was 1, then I need to return 0. Now, if I know that the string size is 1, that means there is only one character. If there is only one character, that means the answer is initially 0. Yes. Do I want any other answer? If there is a single string, then that means the whole string is same. So I will return the answer 0 and I will return from here. Now the other part. Check for S0. If S0 is 0, increment C0, else increment C1. So this is the first base case I've taken, that 0th index, whatever is kept over there, that starts off my segment. Now I'll loop from 1 less than n. I'll check is s of I not equal to s of I minus 1. If that's the case, then I'll check is s of I equal to 1. If it is equal to the character 1, I increment C1, else I increment C0. And this else part is not even written, because I know else I'm not going to execute anything. I just want to continue forward. Yes. And then when I come out of this whole structure, printing the minimum of C1 and C0 is going to give me the correct answer. All right. So I think this is clear. Yes. Can you tell me the time complexity of this? Let's say I want to calculate the time complexity. I can see that I'm only running a single loop, right? In this order of n. Yes, this is the order of n loop that I'm running in the string. So that means time complexity is going to be O of n. This is the highest superseding term in which I am running the solution. As for space complexity, we know that in space complexity, we are not using any extra variables, as in data structure variables. We are only using two simple variables, which will take constant space. So beside the space of string or something like that, you can just say that my space is constant. Is it good enough now? I think the idea is clear. Yes, do you guys have any doubt? If you guys have any doubt, you can just open your mic, I'll answer this. I think it's clear. All right, it's clear. All right, let's move on to the next problem. Yep. All right. So now I think this is the problem that, I mean, this problem technically, like, let's see the problem first. You were given positive integers a, b, and k. And for a variable x with an initial value a, you need to achieve the target value b. In one operation, you can either change x to x plus 1 or change x to k into x. So it's pretty straightforward what they want you to do. It's operations that are given very clearly, and that is something you need to do. Now find the minimum number of operations needed to go from x equals to a to x equals to b. All right. Now a very first look in this problem might seem that because I have two operations to do, maybe I can run sort of a DP structure, right? Maybe a recursion approach. Can you agree to this? Yes. Like, because I have two operations, what I can do is like keep a x variable with me, and then I can maybe increment it. That's one kind of operation, or I can convert it to k into x. This is like one of the straightforward approach that might come to your mind if you have practiced recursion. But the problem is, if you see that the constraints, they're given in a very different order. Now, I don't want to go into the very depth of this, but looking at the constraints, it should make sense for you that it will not work because A and B are in a order of 10 power 9. Yes, because what can happen is, let's say k was given 1 to you. Let's say k was given 2 to you. That's the smallest case. And A and B are very huge. So the recursion call stack to actually go from the recursion call stack, which you would have called to go from x to x plus 1. Let's say A was 1 and B was 10 power 9. Now tell me, if you want to go from 1 to 10 power 9 and you're only considering the tree path which you take from x to x plus 1, then will you not have the depth of 10 power 9 nodes? Can you imagine this? If I, let's say, start from this node, then I'll be going in a depth of 10 power 9 nodes for this call structure, which I would create in the recursion stack. Is that right? So will I be able to like maintain this sort of a sum of a statement. So sum of statement is missing. So I no TC should be less than O of n. Exactly. Like that also makes clear, right? So for all those people who understand this concept that I cannot implement recursion in this part, that is where your next idea should pop up. All right. So Anshuman is asking, what is recursion? I mean, is this a good good area to discuss what is recursion? All right. So I think Anshuman, I'll give you a very small statement on recursion. Okay, I'm in level 1. That I have no problem with that. I'm not trying to point that out. But then this is for all right. Let me do that. All right. So I'll just discuss a very brief of this. Recursion is basically function calling itself. So what happens in this sort of problem is, because you have two options to take, what you can do is you can create a function which maintains some values. Let's say this value, current value, let's say I'll call this current value A, and that's current value, target value B, and then I have a K with me. So let me say I've maintained 3 values. Then what I can do is, inside this, I can call 2 function calls. The same function, I can call it, and I can say A converts to A plus 1, B remains constant, and this is K. And the other function call can be A becomes A dot K, then this is B, and this is K. And wherever I see that, let's say A has become equal to B, then what I can do is I can return the number of count of operations what I had. I can maybe add 1 plus 1 plus over here. So it's kind of a standard recursion solution which gets created. All right, to count the number of operations of what is happening. And out of that, I want the minimum. So like this is the overall view of recursion. Now I don't want to go into depth of it, right? But like it's a very generalized idea of yeah. So just basically just calling function again. Exactly. That's the point. So like these kind of problems where there's number of operations, you have to minimize something. And if the constraints allow you, mostly people come up with a recursion to a memorization approach where they actually maintain some state and where they're able to put out what minimum they were able to receive. So I think besides like this idea is like kind of should have struck you for all the other people out there, if I'm not wrong, right? Do you guys all are familiar with recursion, basic recursion in this case? Yes. So now the problem is this idea won't work as this will give segment for 1. Yeah, exactly. This idea won't work for a test case I just explained you. If let's say I said A is 1 and then B is let's say 1E9, then in this case, the recursion call stack to actually go from A to A plus 1 to A plus 1 to A plus 1 cannot be like it. Even if you memorize that part, you will not be able to maintain a very high state, because even in memorization, we need a complexity that stays in an order of 10 power 6 to 10 power 7. Now that is not going to happen at all because the order is so huge. Yes. So everyone is getting the idea why this is not going to work. And for all the beginners out there who will see this video later on, this also becomes a clarity point of view that I cannot implement something like this directly. So what comes the next idea? Next idea comes is something like greedy. Like you can imagine that I should maybe implement something like a greedy. Let's say I am standing at A, then I am standing at B. I want to go from A to B. Then what you can argue is typically that, let's say I want to make A equals to B, then maybe I can first try to approach B maximum what I can. Maybe I can say that, let's say whatever difference that is there in between of them, I want to cover them. So I'll maybe multiply A with K and so on greedily till I'm able to reach some position which is less than B, and then I increment. Yes, something like that maybe. Or maybe let's say you argue that I'm going to add first. Maybe let's say I'll add 2 times and then maybe I'll multiply with K, something like that. So the whole idea is like, if you try to come up with a greedy approach like this, tell me, can you possibly point out when do you want to add and when do you want to multiply? Tell me this. Like I want to build the induction. I have done this problem previously, like a similar problem previously. And at that time, I was not able to solve the problem. But when I saw the solution, what intuition they proved is what something I'm trying to tell you guys as beginners. All right. So looking at such a problem or looking similar like problems, what should actually strike you what I'm trying to build? Right? If I directly tell you the solution, that's not going to be the point. So I'll like let me ask you this again. If let's say you're standing at A and you want to go at B, is there any feasible way to declare when do you want to multiply and when do you want to add? Like if I'm standing at A, I can be like, all right, my mood is currently to multiply with K, and you can be like, my mood is currently to add 1. Yes. Can we both not argue that either of the way can be proved good. Like it cannot be made sure that I should have multiplied with k or I should have added 1. Or let's say somehow I did prove that yes, this was possible. Then for the next move, again, same argument. How do you know that if you want to add, it's the best thing? Or if you want to subtract, if you want to multiply, that's the best thing. Do you get this part? Greedily, we cannot prove this. Yes, like both these operations are so independent of themselves, which have no like they don't have any thing that is making me sure that I can do this. Is the case why I should not do this. That's actually the argument behind the whole thing. You guys are free to open your mic and like let me know if you think of the idea like in some other sense. I think no, right? Can you you cannot go about this, right? It makes sense for me. You cannot go about to do this, that you are able to somehow come up with a very crude like saying that all right, this is when I should have multiplied and this is when I should have added. All right. So the whole intuition builds up is I am trying to find some operation on which I am sure I can do this and which is greedily going to help me the best. In this case, it's not possible to determine that part. But then let's say I reverse this part. Let's talk about something else. Let's say I wanted to go from B to A. What will happen now? In B to A, obviously the operations are going to reverse as well. Yes. In this case, obviously, if I want to go to B to A, that means you could have either decreased B, that is B minus 1, or you could have divided B by K. Yes, B becomes B by K. Are these the two operations available? Yes. All right. Now tell me one thing. Out of these two operations, like, can you actually argue at some specific, I should say operation that this could have been done only if something was true? All right. So Anshuman is giving an idea. Anshuman is saying that if, let's say, I am talking about the second kind of operation, like first kind of operation can be done anytime, right? As long as, let's say, I am standing at B and I declare B to be B minus 1, as long as B minus 1 is greater than equal to K, I'm good to go. Equal to A, I'm good to go. Yes? But then this operation is feasible if you want to say, like, if you say that, when can I do this operation? You can only argue that I can do this operation only and only when I feel that B mod K is equal to 0. Agreed? Like, can I do this operation to convert B to B by K if I think that B is not divisible by K? Yes. Do we all agree to this? So that is the whole idea behind the problem. I think you're getting it now, right? If you have any doubt, you can again ask this in the chat. I'm there. All right. What I had just said is, in the initial part, when we saw conversion of A to B, we were not able to determine which operation should we use. But then in this part, how to know this is optimal? All right. So Naveen, let's look at it like this. Optimal as in what case? Like optimal as in not doing A to B to B to A or otherwise? Like if you argue that let's say there were some operations which you have followed to go from A to B, then those operations are the same operations you would have received from go to A, B to A. Minimum steps. All right. So minimum steps is something I'm coming to. Like minimum steps, I'm making sure. In that case, like if you argue why would this give me the minimum steps? If let's say you were like initially I think your idea would have been that you wanted to go from A to B. Yes. When you wanted to go to A from A to B, then what did you argue? I think I'm sure that you would have argued that if I want to go from A to B, let me multiply by K. as compared to add 1. I mean, that can be something that you might think, right? Maybe that could have been optimal. I mean, looking forward, the whole fact being that this difference, whatever is the difference between A and B, I want to cover that difference as quickly as possible. Yes, Naveen? Like, I want to cover the difference between A and B as quickly as possible so that A and B become equal. Correct? Now, when I say that I want to go from B to A, why will I say this is optimal? Because if you choose this operation, like if you look at the constraints, you will say that you will see very clearly that K is greater than or equal to 2. So tell me, if B is divisible by K, if let's say B is divisible by K, and B being divisible by K, after you convert B to B by K is still greater than or equal to A. Then out of these two operations, tell me, like you guys can answer this, Naveen, except the other people also, which operation is better? Because I know K is greater than or equal to A greater than or equal to 2 in the constraints. So that, like you can see in the constraints also, I'll show you. Yeah, you can see K is greater than or equal to 2. So that means if I choose this operation, knowing that B was divisible by K, then that would half B. I mean, that would say that, like, if the least possible number that's given to me is K is 2, then that would mean I am halving B as compared to I am subtracting only 1 from B. Now, in both cases, if the numbers are greater than or equal to A, which way am I reaching A faster? In what way am I reaching A faster? Tell me. The second operation, right? Yes, if I make use of the division, then I am reaching A faster. Yes. And then argumentally, when I say that, let's say K was something that was not dividing B, then what could have only been done? Like, you're not left with any more options now. Try to remember this. When I was going from A to B, I was always made available with 2 operations. Was there any constraint on any operation? Like, you cannot do this, you cannot do that, except the part that they should be less than or equal to A if you're going, sorry, less than or equal to B if you're multiplying something or adding to A. But then other than that, was there some added constraint which would have made clear to you whether you want to multiply or add? No. That is why I shifted to this approach. Because in this approach, it was pretty clear to me that I can only do division when B modulo K is equal to 0. And if I don't do division, then the only left operation with me is a very simple and a single number of operation left, that is subtract. That's all. I cannot do anything beyond that. So if let's say B was not divisible by K, that means I will reduce B to the next nearest multiple of K. That is the number of times I would have subtracted B again. 1 from B again. 1 from B again. And I would have made it come again nearest to a multiple that is divisible by K. And then again, I would have said, all right, now I have a number that is divisible by K. So I'll divide it K. I will divide it by K because I know division is always greedily better than subtraction. That I can very well deduce by the logic that K is greater than or equal to 2. So it always seems better to divide if it's possible to divide. Agreed? Do you guys get the logic now? Yes, got it, Naveen? Yep. All right. So again, I'm trying to build the intuition. So always remember, like I'll tell you, like, take away from this problem. Always remember that somehow or the other, if there's like a source or destination stuff or something to something like type of stuff, like I have also observed this many of times, that sometimes there are solutions which are made on rather than going from source to destination, but rather from destination to source. Just on the fact that maybe you were like at the end, if there are some choices, you are not able to implement recursion on DP, then that means there has to be some greedy part. And if there has to be some greedy part, you need a very concrete structure to actually build a greedy solution. And in this case, if I wanted to go from A to B, I will never be able to build a greedy solution because I know there is no concrete way of selecting out of the two. But then if I reverse my part, I know there's a concrete structure. So do you guys understand the takeaway from this problem? Like, if I've told you now the solution, the code is going to be pretty simple, but then the takeaway should be very clear. Yes. Main thing was to think backwards. Intuition was hard as I didn't correct. Exactly. That's all right, Naveen. So all the beginners out there who must be seeing problems like this for the first time, this is a learning part for you, right? We as mentors are there to tell you the solution in such a way that you guys are now able to think of the intuitions later on, right? So I'm not keeping you binded to this problem itself. Rather, I'm trying to encapsulate all the part together that source to destination problems are kind of like this only. Thinking backward sometimes help. That's the whole deal. All right. Even if K was 1, answer would have been B minus K. Yeah, I mean, if K was 1, then the answer is B minus K directly, obviously, because if you multiply or you add, both are same thing, right? Like, if you multiply, it's not going to be help you at all, because then the number is as it is, and then you want to add. Yeah, Vishal. So K being 1 is not the big deal. Because K is 2, then the whole problem starts new. Right? Yes, I think you get that part. Yeah, you have written otherwise your solution. All right. So is there any doubt in this? Like, now we can actually jump to the implementation, but then implementation can be done in any part. Once you've understood the idea, maybe you can pause the video here and you can go out to actually code this up yourself. All right. Greedily choosing how do I divide and how do I multiply? Sorry, how do I divide and how do I subtract? What should I subtract? How is the nearest K multiple getting formed? And so on. Again, I'll try to run this on a test case to show you, but then let's look at the code part. Good to go? Can we look at the code? All right. Yep. All right. Cool. All right. So I think we are in a good speed for now. Yeah. Again, sorry for the boilerplate stuff. I'll just try to picture out all the code separately, and then things are going to look much more clear. I mean, it's just mathematics, and I used basic macros, but then people out there on the channel might get a problem on this. All right. So yeah, I think everything has been. Let me see. Yeah, this is not clear. Long. Cool. Now I think the solution should look clear. All right, so I've taken the input of A, B, and K. Let me just try to run this and see if this works. Yeah, it works. All right, so A, B, and K. Take the input of A, B, and K. Now I am running a while loop that says till A is not equal to B, I want to do something. Is this clear? Till A is not equal to B, I want to do something. Make sense? Now, first hand check would be simply if B mod K is not equal to 0. Now, if B mod K is not equal to 0, that means I'm only going to subtract. Yes, that is the only thing I can do. If B mod K is not equal to 0, that means at this particular position, I would have reached by adding. So in the reverse manner, I would have subtracted. And where would I have been subtracted? Like greedily, I would have subtracted to the nearest multiple of K. Agreed? Do we agree to this part? So now how do I calculate this? Like if you guys understand integer division, you will very easily be able to see that. First, I've calculated a small variable called f. All right, I'll just zoom into this part. A small variable f. Now, f is actually b by k. What does this mean? What is this going to give me? It's going to give me the nearest device. Sorry, it's going to give me the nearest multiple that comes up. No, sorry. It is going to give me the nearest value that I could have actually received from the multiple. Yes. Let's say in this case, I'll give you a very small example. Let's say I have 11 as b, and then let's say k is equal to 7. Then when I'll divide b by 7, I'll divide 11 by 7. What I'll gather is 1 by integer division. Yes. And then when I multiply this again by 7, what will I gather now? 7. So I know from 11 to 7, this 7 actually is the nearest multiple to 11. Can you get this idea? Do you get this idea? This is what I've done over here. I mean, you could have written this directly in one line, right? This is a like straightforward mathematics. You can write it like this, but that's not going. That's something I did not want to do. So I'll divide b by k. That gives me that part of multiple, and then I multiply that with k. So that gives me a new value. That is the nearest multiple. So this FF is actually the nearest multiple. I'll rename this nearest multiple. All right. Now, how much do I want to add in my C? This is my operation count. I can maybe name this OP. How much do I want to add in my OP? That's the operation count. B minus nearest multiple. Yes. Do I want to do that? Because that is the number of times I'll be decreasing B. Or in the inverse order, I would have actually added on to B. Added on to A, sorry, to go to B. Are you guys following up till here? And then when this happens, I will finally make B equals to the nearest multiple. Agreed? Because now I know that B has reduced down to the nearest multiple. I think this is clear. Yes, this is clear with everyone. If it's not clear, you guys are open to, like, you're free to open your mic and or put this out in the chat. All right. All right. Now the other part being that if I don't go in this if block, that means B modulo K is 0. Yes, that means B modulo K is 0. So now what I want to do, now what I want to check, now this is something like this might be become a corner case. If B mod K is 0, that gives me two options. I know I want to divide it by K, ideally, but then if I want to divide it by K, I want to still keep the value greater than equal to K, greater than equal to A, sorry. Yes, this is what I wrote over here. If I divide B by K, then the B by K value should be greater than equal to A. What if it happens that you go below this, below A? Then dividing by K was not helpful, right? Do we agree? Like, if it's possible to divide B by K, if it was possible to divide B by K, the current B by K, but you went below A, then will you ever be able to come back to A? The only other operation available to use to subtract B. So if you go below A, you will never be able to increment B. Do you get this idea? Like, let's say let's say B was 6, and let's say K was 3, and let's say A was 4. So I know that K divides B, but then if that happens, B becomes 2. And now B can never become A, because B only can subtract or divide. It can only reduce its value, to be specific. So will I do this? I won't do this. So that is the case I've handled over there. Can you all agree with this? Like, if you have any problem, you guys are free to open. If I'll not get any response, I'll move forward, but then that can be an issue. So what I'll say is, if B by K is greater than equal to A, that means doing B by K is feasible. So I'll divide B by K and I'll increment my operation. And the other else part finally would be that if I don't go in if, and if I don't go in else if, that means B modulo K was 0, but then B by K did not give me a value greater than equal to K. It would have given me a smaller value. So if that is the case, then I know I cannot further divide it by K. Only best possible option left is to do operation plus equal to B minus A. That's the leftover difference between that, to showcase that B would have subtracted to A by this number of operations and break. Because after this, I know B has definitely become equal to A, and I can stop. And then I can print operation. Got it? Is this clear? Let me try to dry run this on a test case. All right. Let's say we'll talk about this. All right. 3, 7, and 2. I start off over here. I say, all right, 7. This is A, this is B, this is K. B divides, like, K divides B. No, it doesn't. Does it? It doesn't. Yes. So I'll say, if that doesn't happen, let me make it come to the nearest possible multiple of K. The nearest possible multiple of K is actually 6 from 7. So that means what I'll do is I would have divided 7 by 2. This gives me 3. Into 2 again, this gives me 6. 7 minus 6 is equal to 1, and I add this one. And then my 7 turns to 6. So now B gets separated and B is 6. Yes. Now I'll say 6 by 2 can be done, and 6 by 2 is actually greater than equal to 3. That's A. So still feasible to do operation plus plus, and that this is where I end, because I have one operation from here, one operation from here. Total operation becomes 2. And then now I know 3, the value of B has become equal to A. So this while check, A not equal to B will break. And then I can come out and I'll say OP got printed. That is, I think, yeah, 2 operations. All right, good to go. Now tell me the time complexity of this. Can you guys think of time complexity of this? Like, what is the smallest log K? All right. What are you dividing? You're dividing B, right? So should you print your complexity in log K term or log B term? It would come in log B term. Yeah. Yep. Like, when you divide N, like, do you guys remember the problem when I want to divide, like, if I want to find the bits in N, then I divide N every time by 2. So what do I say? I get a log base 2 N solution. Yes. Where I know that the division factor was 2 and the number I was operating was on N. So in this case, what am I operating on? I'm operating on B. And removing the subtraction part, the best possible division case which I'm taking is dividing by K. So that means I'm running in a factor of log with a base of K. Agreed? So I'll say the complexity here is log base K. Like if I write this like log base K of B. Agreed? And then what is the space? I'm not using any extra space, so I can say space is constant. All right. I think this is clear now. Yes? Agreed? Can we move on to the next problem? All right. Cool. All right. So now in this problem, like, all right. So this is a graph problem. That was very clear, right? That means being it a graph problem, I'm assuming that you guys will understand some prerequisites of graph. Yes, generally, what is node, what is edge? So I'll not be going to explaining what is a node, what is an edge, how does a graph look like. All right. And then because this is a graph problem, prerequisite of this graph would definitely be to understand what are the general algorithms that are out there in graph, right? So I'll dictate as I go. In this problem, you were given an array of A of size n and a complete weighted graph with n nodes and n into n minus 1 by 2 undirected weighted edges connecting each pair of nodes. All right. So that means if I have, let's say, 1, 2, 3, 4, 4 nodes, then everything is connected to everything. 1 is 2 to 2, 1 is to 3, 1 to 3, 1 to 4, 2 to 3, and I think 2 to 4. Everything is connected to everything. So that is why you can say that I have n into n minus 1 by 2 edges. Do you all agree to this? Yes. This idea should be clear, right? And then this edges have weights. And the weights are defined by a very, very interesting factor that if you join, let's say, the node I and node j, the value of that weight edge is going to be absolute difference into max of aij. All right. So let's say I join, let's say I have 0 indexed nodes. So let's say I join 0 and 3. So this would be 3 into whatever is the maximum value kept here. Let's say 5 value and 8 value. So I'll say 8. So the edge that joins is going to have a weight 24. This was clear. I don't think there's any problem in this. Yes. Now, distance between two nodes is defined as the minimum sum of weights on the path connecting two nodes. Again, very simple to understand. I have the minimum weights on the path that I'm trying to fulfill. And find the distance between nodes 1 and n. This is what I want to do. So now, when you look at the problem, you will very clearly see that this seems a shortest path problem, right? Are you guys all having a basic prerequisite in your mind that shortest graph problem is like the algorithm Dijkstra maybe comes to the mind, right? Dijkstra is a very, very, very popular algorithm to solve shortest path on a graph. Yes. I have not done a single problem on graph. Is this beginner friendly? No, this is not at all a beginner friendly problem. All right, Vishal. So I'm sorry for that. Like this problem is going to be a bit hard for beginners because then this requires graphs, understanding of graphs. Then it also requires understanding of why an algorithm like Dijkstra or shortest path won't work, and then why are we coming up with the other problem? All right. So it would definitely require that, but I'll try my best to keep it as simple as I can. And anyone who's watching this video, all right. All right, cool. So there is something known as a Dijkstra algorithm, right? Which actually helps us to calculate the shortest path algorithm. Now, I can give you a very clearly written part in this part that Dijkstra algorithm, like for just assume that for I'll tell you that Dijkstra algorithm in a worst case complexity, like if I'm talking about a graph, the graph will have some number of vertices and some number of edges, or some number of nodes rather, you can say n nodes, and let's say e edges. All right. For any graph algorithm, it's impossible to solve in one. Correct, exactly. That's what I'm coming to. So in a generally, like if you form this graph very brute manner, so even if before you go to the Dijkstra part, tell me, will you be able to create this graph? Like this graph is not given to you directly. Yes, you are given only the array. So you will have to sit down to create an adjacency matrix and actually join the nodes. Agreed? Do you agree to this? Like I will have to actually run an iteration on all the nodes. like all two pair of nodes rather. And then when I know that what node am I at, let's say I'm at node ing, then I know I can join them with a edge value, and that edge value can be very easily calculated because that is in a constant time. That is very clear. But then the argument is to actually create this graph. How much complexity will you require? Because you want every pair to be contributed, you will like have a very brute solution that looks like for loop over here. This is an I iteration. And then inside this, you will have another for loop that is of the j iteration. This also runs to n, and this also runs to n. Yes. So in this part, the creation of graph is going to take n square itself. And then after the creation, the Dijkstra or then any shortest path algorithm you actually have is going to run in a v square complexity. Like the a Dijkstra written without priority queue is in v square. And if you have a priority queue, then you have v plus e log v, which again, if edges is in n square order, then this would again go in n square. So this v also being like would go in n square. And this is again n square. So like even the creation, even the running of the Dijkstra algorithm is going to give you an order of n square solution. Do you agree to this part? So in an n square solution, will you be able to solve this problem? Like, you know, n is in 10 power 5 order. So I cannot run an n square solution. Yes. All right. So I'll tell you by experience, like what happens in this kind of problems is, takeaway is most of the time, problems like this where you identify that there are a lot of edges. What is the main problem in this? There are a lot of edges. A lot of edges. Is that right? There are a lot of edges. That means I don't want a lot of edges. Because I have edges that are in order of n square, it is making me a problem for me to run this shortest path algorithm, or to typically just imagine that I'm running an algorithm. Yes. So because my edges are a lot, I need to somehow lower the count of edges. Now, if I want to lower the count of edges, it is very clearly given the problem that there were possible n into n minus 1 by 2 edges, because you could have attached every node to every node. Agreed? Yes. Every node to every node could have been attached. But then if the intuition is kind of built in that part that I want to somehow decrease the number of edges, that means somehow in the problem, there is a hidden, like there is some hidden observation, which is eventually going to help you understand that I have some useless edges. That means even if I don't consider these edges, I'll be good to go. Like I don't need these edges to create the shortest path. Are you getting this idea? Like, are you getting the intuition I'm trying to build? If there are n square edges and I know I'm trying to run a algorithm below this, that means somehow or the other edges have to be removed. And if edges are to be removed, it makes sense that those edges must be useless. Because if I remove them and my problem is not able to solve, like if I remove them and I don't get the right answer, that means that edge was important for me. But if I'm able to still get an answer, that means it's a useless edge. So if you are somehow able to determine a useless edge, if you are able to figure out that I can take a useless path, like useless edge path, then we'll be good to go. Right? Or to be very specific, if I figure out what useless edges are there, or how can I actually connect in such a way, like the graph can be connected in such a way, such that I don't cover n square edges, but rather I cover edges in an order of n. In an order of n. Then tell me, will you be able to run a straightforward solution? If like you somehow bring down the edges count or the edges order in n, then you will be able to bring up a solution. Yes. So this is the whole idea behind the problem. How do I get the thing going that I have some useless edges? All right. So do you guys have any idea for this? Like I want maybe some ideas. If you guys have any idea. No idea. This was tough. I mean, agree. Like this was also, like, this was tough generally. And like, this is a greedy problem now. Because when you have to, like, as I said, do you all agree to this part? Then when I said there are some useless edges, that means some edges becoming useful for you. So because some edges becoming useful for you, it means it has the greedy approach. Like you can greedily choose which edge is becoming useful to you. Do you agree to this part? Yes. If I'm saying that some edges are useless and some edges are useful, that means somehow or the other, you're able to determine which edge is useful. That is why you're only saying this. And that kind of makes this problem a greedy problem. Yes, by seeing the constraints, I can confirm it was greedy. All right, makes sense. Like if you look at the constraints and you are able to figure that out, good enough. So is everyone catching up till here? What idea was not there, what was possible, and so. All right, cool. So now I'll start like making some statements and like tell me if you're able to catch up with this part. Now, like the first thing is very obvious. Like, let's say you're standing at some edge. Like, let's say you were covering a path. So let's say these were the nodes. I've written them nodes directly forward. Let's say this is node 1, 2, 3, 4, 5, 6, and 7. Let's say there are 7 nodes. Now, let's say you start off, you have obviously have to start from 1. So let's say you start off from 1 and go to 4. And now you argue that from 4, I want to come back to 2. Or rather, come back to an edge, or come back to a node from 4, which is before 4. Do you think that is going to be feasible? We are running a greedy part. So I'm trying to like boil down every idea together. One idea at a time. Like if I start off with 1, and let's say I just went to the node 4. From node 4, my argument is like, do you think I should have gone back? Like, should I take a step back to go back to node 2 and node 1 or node 3? Somewhere, let's say I go back to node 2 only. Should I go back to node 2? Or should I only move forward? Hello? Like, am I not audible? Like, I think I'm audible, right? Forward. All right. So Praveen is saying forward. Yep. So I'll try to give you a very small, like, generalized part of this. All right. So like in this case only, I'll try to fill up some values. Let's say we can even prove this out maybe. All right. Only forward. All right. So Yash is also saying only forward. All right. So let's say I'm standing at 4 and let's say the value kept over here is 5. All right. And let's say the value kept over here is actually, let's say 6. So if I would have moved backward, like up till here, whatever cost was there, let's say the cost was X. Now, when I move backward, what is the maximum of these two? 6. So I'm taking the case when I say that, like, if this is I and this is J, I moved on to, or I can take it like this. Yeah, this is I, this is J. So I moved on from some I to J. I moved on from some I to J so that I know that I was greater than equal to J. And then I'm assuming that when I did that, only 2 possible cases are there. Because when I do that, I am seeing this edge value. Now this edge value is kind of dependent. Like I know because I'm moving from I to J, I minus J is constant. Like this absolute I minus J is constant. Yes. Into I have max of these 2 values, whatever was kept as AI and whatever was kept as AJ. So I only have 2 possible cases. Like this dependence is gone because I know that's fixed, I and J. What can vary is either AI is bigger or AJ is bigger. Only that can vary. Yes. So in this case, let's say I have taken AJ to be greater than equal to AI. I have. Yes, I've taken 6 and I have taken 5. So maximum would be 6. What value will I get over here? I'll get a 2 into 6. That is equal to 12. Yes, I will get a 12 over here. Now, from this 6, next time, is the meeting and audio lagging for me or all right? Is that happening? You guys can tell me. Like I might be sitting in a. All right, no for Praveen. Is my audio and video lagging? Not lagging. All right, cool. I think it's not lagging, right? It's all right. All right. Now, let's say in this case, I took that AJ was greater than AI, and this is the extra cost 12 I incur, right? Now, from this J, now again, let's say you move on to some next element. Now, this was a backward move kind of you did. Now, let's say you did not do this backward move. And now from J, you want to go to some other K. Like, let's say a new position K. Let's say, and that is a forward type. So let's say maybe you jump from this to this part. All right, this part, this is K. Cool. Now, when you do that, you have some value maybe kept over here. But then tell me, like, let's say you jumped to this 6 value, right? Compared to this, like, now the next time what will happen is this K, being that like this is AI, this is AJ, and this is AK. What can now be proved further? 2 cases can come from this part also. When you move to AK can be greater than equal to AJ, or it can be less than AJ. Yes. So I can say when I'm at AK, if let's say I say that AK is greater than equal to AJ, then AK will superpower. AK is going to superpower over AJ. So I'll be multiplying the difference from 2 to 6. Yes, multiplying the difference from 2 to 6 into AK. Is that right? Do we get this? The difference into AK, because AK is bigger than AJ. Now tell me, initially the case I said was AJ is greater than AI. Now if AJ is greater than AI and AK is also greater than AJ, then AK is definitely greater than AI. Yes. AK is definitely greater than AI. That means let's say a value 7 was kept over here. If 7 is greater than 6, 6 was greater than 5, then 7 is definitely greater than 5. Yes. Agreed. So in this case, I think you're able to catch up. If you're not able to catch up, please stop me. All right. This is a very greedy, intricate proof. All right. So it required some case thinking. So I'm trying to go as low as possible. All right. I'll try to repeat this once more. You are at AI. If you take a backward move to some number AJ, I have made 2 cases. This is case 1. Case 1. Case 1 is when you move to AJ, that was the back move. Let's say AJ value was greater than equal to AI. In this case, the cost would have been multiplying the difference, that was this difference, that was 2, into this bigger value. Bigger value was 6, so I got a difference 12. Good enough. Now, in this case 1, I have made 2 subcases again. These 2 subcases actually are telling me that what if after now AJ, I move on to the next element in the forward direction to K, where AK was kept. That can happen is AK is greater than AJ or AK is less than AJ. So I'm trying to analyze both cases. Now, if I say AK is greater than AJ, because AJ was greater than AI in the first place, AK will also be greater than AI. And in that case, now tell me, if AK is the biggest term of AJ and AI, then did it make sense for you to move from I to J to K? Can't you have not moved from I to K only? Will that not have given you a smaller cost? Agreed. I went from I to J, I got it cost 12. Next time from J to K, I'll again be covering this difference with a cost of AK. That is like 7 into this difference is going to be 4. So 4 into 7, 28 again. Is in compared to this, shouldn't I have simply said, why are you going backward? Move from I to K only. Move from I to K, difference only will be 2. And the highest value is 7. So 7 into 2, that's 14. Compared to 12 plus 28, 14 is a smaller value. Yes. So will it not have made sense for me to move directly from I to K? So this is part 1 checked. If case 1 was AJ is greater than AI, then in that the subcase 1, that AK was also greater than equal to AI. In this case, I have counteractedly proved that it would have been better for me to move from I to K rather, not gone back to I to J, then go to K. Agreed. Now let us take a different. Now, subcase 1 is done. Let's take subcase 2. Subcase 2. AK is less than AJ. So AK is less than AJ. Let's make some value. Let me say let's modify some part. Let's say this value was 7. All right. Let's say this value was 7. So let me take this value as 6. Now I'm good to go. Now in this case also tell me, can you see the best possible answer? It again makes sense, right? By the same counter logic, if I move from I to J, the cost value that will incur is the 7. And then when I move on from this J to K, the cost value that will multiply, this 7 is going to be a problem to me. Compared to which, now of the 7, if I don't even consider 7 and I would have moved from I to K directly, it would have only counteracted the values with 5 and 6. So the difference would have been much smaller. and the maximum of these two values would have been much smaller, making this edge value the smallest. Yes? Are you guys following up with this approach? Hello. I think many people have left. All right. So what I'll do is like I'll just try to continue. All right. And you guys can break or stop me wherever you feel you're not getting the part. All right. I'll try to be as slow. So all right. So I've covered this case now, making sense that if I'm standing at an I, and if I actually go backward, in any of the case, it's bad for me. Yes, because if I went backward, if I go backward and AJ was AJ was the greatest of AI and AK, then also AJ would have been a problem because it would have turned him in the max element case. In the max of AI, AJ becomes max, and then from AJ to AK, AJ again becomes a problem. So AJ will overpower AI and AK, and that would make my total path length very huge. Compared to which I could have directly followed the path from I to K, it would have definitely given me a shorter length. Yes. And otherwise, if let's say AK was the biggest part, then also it made sense because I know that in that case, it made sense for me to create the shortest path first, like shortest difference first. So from I to K, I is closer to K. Why go backward to J and then to K if I know that the difference is going to be much more huge? So this term will go very huge. If this term goes huge, then also that's a problem for me. So the argument is no matter what the next move is, it is not going to be like, it will not be more expensive to replace. Like I'll state this out. If you move from I to J, where I is greater than J, all right, and A of J is greater than A of I, then no matter what the next move is, like no matter what, wherever you land from J to K, it is not going to be more expensive to replace I to J to K with I to K directly. Are you guys following up with the approach now? If you want to go from I to J, where I is greater than J and AJ is greater than or equal to AI, and after that, whatever move you take from going to J to K, you can always choose this over this. All right, I think this is good to go. Yes. Now I'll take the next part of this. Now I'll say that AJ is less than AI. What happens if AJ is less than AI? Then also you can figure this out, right? If AJ is less than AI, then can you argue the same part? Like if let's say in this case only, I had this value, like this value was not 7, let's say this value was 4. Then from J, if I move on to some K value, then do you think it would have been feasible for me? No, right? I mean, I'm not going to try to make a case for this because again, on the same ideology, you can prove this out. Yes, or should I make a case for this? Like, I don't think it's needed to make a case for this once I've explained you this part. Like, if you are able to understand the case for AJ greater than AI, then you will be able to make a case for this also. No, correct? It's okay. All right. So people in the chat are saying also it's okay. So I think I can move on. So up till here, whatever discussion we have done, how is this helping? Like this discussion, what did it help me to analyze? It helped me to analyze that I only want to move forward. Forward is the way to go. This is proved. Yes, that means I don't want to go backward. Meaning if I'm at an I, go to some J, go to some K, go to some so on, so on, so on. Knowing that J is greater than I, K is greater than J, and so on, so on, so on. So the movement has to be only forward. Now, if this is clear, let us try to come up with the next part. Now, when you are obviously standing at A1. This is the first, you are standing at node 1. You begin with node 1. Yes, you begin with node 1. That means the current value you have is A1. Agreed. Now, from this A1, the next possible values are, let's say I have taken a 7-sized array. So this is 1, 2, 3, 4, 5, 6. Right? This is node 2, node 3, node 4, node 5, node 6. And they have the values kept over there. Now I'll divide this again into two cases. Now, one thing is clear. I only want to move forward. Yes, I only want to move forward. Now tell me one thing. From A1, if let's say there is an index at this location, in these 6 places, there is some index, if this is I equals to 1, if there is some index j greater than I, all right, where AI is less than equal to A1, then what should I do? Like, let's say I'm standing at some position. This is the first position I'm standing at. And on the right hand part of this, I found a number that is smaller than this A1 number, smaller than equal to this A1 number. So tell me, what should I do? I know that if I would have traversed that edge, if I would have taken that edge with me, then let's say I I would have jumped to A4 number. I know that A4 number is less than equal to A1. Then tell me, if it's less than equal to A1, what would have happened in the max of A1 and A4? In the max of A1 and A4, A1 would have dominated because A1 is greater than A4, greater than equal to A4. Yes? Do we agree? That would have been the case. So in this case, like, tell me, for all such possible j's greater than I, where like this is greater than I, so I is 1, all right? So I have taken 1 actually, right? This is j is greater than 1. So for this, all this j greater than 1, where aj is less than equal to A1, I should have actually jumped to that part. As in, like, if I would have wanted to jump to that part, which best case should I have taken? Tell me. Like, let's say the numbers A2, A4, and A6. All these 3 numbers are less than A1, less than equal to A1. Then out of jumping to A2, A4, A6, where should I have jumped? I know that the maximum of A1, comma, A2, or A4, or A6 would have still given me all A1. So A1 has become fixed. The maximum part has become fixed. The leftover part is absolute of I minus j. This is the left part. Yes. Now tell me, if this is the left part, A1 has become fixed, should you not take the leftmost index? If this is index 2, this is index 4, this is index 6. If A1 is the fixed value over here, then if I want to make this the smallest now, like if I want the smallest, shortest path getting added, then should I not take 2 out of this, or rather A2 out of this? Yes, agreed. Because if I take A2, A4, A6, this term is not going to change, this term. Because the maximum of A1, A1, A2, A1, A4, A1, A6, all is going to give me A1. Because I know all these numbers are less than equal to A1. But then the thing that can change is this part. I have a control over this part. So why not, if I have a control over this part, let me not, why should I not take a number that is closer to 1? The index that is closest to 1. So should I not jump to this part? Do we get this greedy approach? Yes, it would have not made sense for me to jump to A6 because I know I would have then created a difference. Like if this is 1, this is 6, it would have been 5 into something. 5 is big. But over here, I only have a difference 1. So this is 1 into something, and that something is constant. That is A1. So compared to this is smaller. I should obviously go with this greedily. Do we get this idea? All right. I think we have gotten this idea. I have talked about a lot about this. Now I'll take the other part. Now I talked about a case when I said greater than j is greater than 1 and age is less than equal to A1. Other case obviously is age is greater than A1. Then what should you do? So you're standing at the node 1. You have 6 nodes, 6 left next nodes with you. This is A1. What should you do? So let's say, I mean, first of all, like, point being is, if you are standing at A1, then this approach should be followed when? Like, when should this approach be followed? I should obviously follow this approach whenever I receive a number less than A1. So if there is a number less than equal to, sorry, less than, not less than A1, if there is any number less than equal to A1 in the right area after A1, then I should jump to that index out of all such indexes, the minimum index. Does this make sense? So supposing that there exists an j greater than 1 such that age is less than equal to A1, I will choose the leftmost index and I will jump to it. Now the other part is, if I was not able to find any index, not found any index, j greater than 1, where I feel that aj was less than equal to a1. That means every number after j equals to every number after 1 index, 2 index, 3 index, 4 index, 5 index, 6 index, so on, right? 2, 3, 4, 5, 6, 7. All these 6 indexes had in the number greater than a1. So if let's say this number is 3, let's say you had 4, 5, 6, maybe 10, maybe let's say 5, let's say 4. Every number was greater. Now tell me, what should you do in this case? Where should you jump to? Obviously, you know that maximum of like 3 comma something has to come here. And every number is greater than 3. So I have to take some number which lowers the expression. And then I have absolute of 1 minus something over here. That's the index. Minimum of the number. Exactly. Correct, Harsh. Exactly. That's a great idea. Out of all this jumping part, if I say I'll argue, if I want to jump to 5 or 6 or 10, will that be feasible as compared to jumping to 4? It would be feasible, yes. Because it would not be feasible. Yes, because I know that if I jump to 4, this expression is going to be very small. If I would have jumped to 6, let's say, so this expression would have given me 6. Max of 3 and 6 is 6, correct? So as compared to 3, should I not want to take the next lowest number? So the next lowest number to 3 is actually 4 on the left right hand part. And out of these 4, I have 2 places where 4 is coming. Out of these, which 4 should I take by the same first argument? Will I take the 4 at this location or this location? Tell me. If you have fixed 3, 4 over here, now you have the control over the jumping of the I and j. So if this is 1 minus where, what should come over here? 2 or 7? Obviously 2 should come over here, right? Meaning the leftmost index on the right part. Are you guys following up till here? Directly jumping to the last won't be also feasible. So we'll jump to the index with the smallest j present on the right. Exactly, Harsh. So argument would be that if every j greater than 1 has a value greater than a1, then I should jump to the minimum out of all the values on the right part. And of those minimums, if there are multiple minimums coming, then I should jump to the leftmost part. So the minimum out of this structure, this part was 4. Out of 4, 5, 6, 10, 5, 4 values, minimum was 4. So I will jump to 4. But then which 4? This 4 or this 4? Obviously the 4 that is closer to 1, because that will again reduce this fraction of 1 minus this part. Are you guys following now? Yes. So if now I have somehow now I have calculated the best possible answer for all the cases starting from 1. That means 1, I would have deduced that the best possible case was to jump to, let's say, 4. Then can I not now treat and now I know that I don't want to go backward. This is something we discussed in the first part. So from 4, I should not go backward. That means from 4, I now want to go further in the forward direction. So now this is again a new problem. Yes, you can pretend that this A4 or this 4 index was your first node, and from that same logic again, as compared to A4, which is the best possible case that comes in the next part, and so on, so on, so on. Agreed. So it's kind of saying that you somehow figured the optimal jump for one, and then you can repeat this process for jumping so on to the next possible indexes. Do you all agree? Yes, greedy jump. All right, greedy jump. All right. All right. So now what have we boiled down our approach? Now, again, this is where things are going to like up till here, if you're able to get the logic, now the point is implementation can be done in any format. All right. Now, I did an implementation with a stack approach. All right. So I'll try to kind of declare, like I'll try to dry run the stack approach with you so that you're able to understand what is I trying to do. I was trying to create basically a monotonic stack of a decreasing to increasing or a directly increasing format in the values. I'll show you by test cases what I did, but then you will find multiple solutions to this. All right. So you can actually create the nodes and run a digestra. That is also one solution. In the, I think, editorial part of this problem also, you will find that there is something as a computing prefix and suffix part. That is also one solution. All right. So whichever suits you forward. Again, I don't want to discuss every solution because this is not a beginner's problem at all. All right. So this is up till here is something I wanted to tell you guys. After this becomes kind of a small up solving for you that you figure out how can you implement this out. All right. I have given you the greedy structure that this is something you have to follow. This is something you want to do. Now, you have to obviously do this by some or the other format, and that format can be anything. So are you following up till here? Is the idea up till here clear? I want to be clear on that, because implementation is not going to be a problem for people who understand the idea. All right. Cool enough? Clear. All right. All right. It was clear. All right. All right. Good. So now, again, one thing in this was like, after you've understood the what we did was, you will somehow see that, tell me, like, if you are standing at some A1, you are only moving to an index less than, like, if you're moving to some index AJ that is less than A1, you want to move to the index AJ that is less than A1, the best possible index that is less than equal to A1. That is one case. And if you want to move to that, it should be on the left part, like on the most left-hand side. Is that correct? Yes. So can I say that I want to move to the next smaller element? Yes, I want to move to the next smaller element, which is almost like the next smaller element, which is closest to the left side. And for this part, like this step, can I say that I want to move to the smallest element? I don't want to move to the next smallest element. I want to move to the smallest element, but that smallest element should also be on the left part. Agreed? So, and like in this case, let's say there was 5 over here and this was 4. So the next, like if this value would have been, let's say 7. So from 7, like I would have, like, all right, not 7 actually. Let's say 3. Yeah, even took this value. Sorry, I'm sorry. This was the value. I got confused with green pen. Let's say this is the value 3. The next, like the next smallest value in this area is 5. But that is not the next, like that's the next smallest value. We want the smallest value, and of that you want the left part. So that is clear. I just repeated my ideas again. Brief done. Now let us try to look what we want to do in that part. Now, if you carefully observe, what you're trying to do is, if you are standing at A1, like I'll take a new page. If you're standing at A1, you are only moving to some number AJ if it's less than equal to AJ. All right, that's the case. And then you are going upward. So the pattern, like the pattern of moving is actually somewhat like this, that you are going either down and then moving up, or you are going only up. Like from A, like the like these, when I say going down and moving up or going only up, this is the value part, what I'm trying to tell you, right? These are the values, like this is A1, A2, A3, A3, so on, so on, so on. So let's say you select the best values. Let's say you selected that, you somehow knew that best was to take A1, A3, maybe some value more, maybe let's say, and then final value AN. Then the argument is that, sorry, moving from 1 node to 3 node to let's say 5 node, and then let's say to the node, final node, N node. Then the argument is the values of this, like A1, A3, A5, AN, either they will decrease first and then increase, or they will only increase because of this greedy approach. Yes, do you all agree? So this is what I have done. Like I have tried to maintain a monotonic stack sort of a structure, right? And I'll tell you my approach. Monotonic, got the wrong spelling. Monotonic stack sort of a structure, or not exactly monotonic specifically, but it's like it's decreasing first and then increasing if that's the best possible case, or either it's only increasing if that's the best possible case. And I'm maintaining two stacks. One stack is maintaining the values for me to actually declare where do I want to jump, and the other maintains the indexes, showing that this is the node I should have jumped to. So indexes are nodes basically. Yes, if I'm talking about A1, that's the first index, first node, and so on, so on. So that is what I'm trying to do. Are you guys getting this idea? So can I move on to the implementation? Like I'll show you the implementation. I'll dry run on one code, one test case, and you will clearly understand what happened. All right. All right. All right. So this is what I've done. I have already also printed this out for you. So I'll just like comment this out first, and then I'll print this and show you what is going to happen. All right. So I've taken the input, right? I've taken the input. This is the input of n. Let me declare this int n, and this is sin n. Then I have a vector. This is the vector of long type. All right. And then I take the input of this. So I have for int I equals to 0, I is less than n, I plus plus. Then I'll take the input, sin a of I. All right. Now I have like, let me just remove a bit of these macros. Yeah, I think that is all there. I think just a second, one long. I have, yeah, long. Cool. So now what I'll do is I have created two stacks. One is the value stack. I'll call this value stack. All right. Let me just values stack. All right. And then this is the indexes stack or the nodes stack, in which I'm maintaining what nodes do I have. What nodes am I connecting? So these are the two stacks with me. Now what I'll do is I will run a loop for int I equals to 0, I is less than n, I plus plus. Now initially I know that I only want to do pushing or popping from the stack to maintain the monotonic structure when the size of the values is greater than 1. This is the first definition. This is the first part. Because I know, let's say the first node came. I know that the first node has to be pushed. Can you not push the first node? Like you are obviously starting from the first part, right? You're starting from the first source node. So can you skip that node? You cannot skip that node, right? You want to start from that. So this while loop is only going to get followed after something has been done. And that something is basically, first of all, we push AI and I in this. So this clearly dictates to me that the first node has been pushed because currently values the size was 0. Are you following up till here? Yes. Now what happens next? Next time a new node comes, that node value, currently the value size is still 1. It's not greater than 1. So I'll still push it. AI gets pushed and I gets pushed. So that means, let's say that would very clearly dictate that, let's say I'm talking about the, where did my pen go? Yeah. I'm so sorry. I think I lost my stylus over here. All right. Oh my God. Just give me a second. Just give me a second. All right. Let me just mute myself. I don't think that's going to be a problem. Just give me. Yeah. All right. So sorry. So sorry. I'm back. All right. So what I'll say is, I would have pushed the 0th node and the first node. Yes, because before that, I know value size was never greater than 1. Agreed? Yes. So I'll start taking this case. I'll talk about, let's say, this case only, 2, 4, 5, 2, 3. So I would have pushed in the first stack 2. Then and in the other stack, I would have pushed 0. That's the node. Then I would have pushed 4. And then this is the node, that is 1. Following up till here, this is stack 1 or the value stack. And this is the index stack. Now what will I do? After this, when a new value 5 comes, this new value 5, I know that currently this new value 5 is greater. Yes, this new value 5 is greater than whatever was kept at the top of the stack. So up till here, the best, like 2, 4 in the up till here, the array 2, 4, 5, if I would have asked you, what is the best possible case of choosing an increasing order? Like, can you create a monotonic decreasing order in this? You can only get an increasing part. So, 5 should have been kept because of this part, because of this argument, which we showed, that if I have like up till here, if I'm moving from A1 to AJ and all AJ is greater than A1, then I'm only adding and I'm taking the next best case. So next best case is automatically with me. Yes. So I'll push back 5 in this. So now I have pushed back 5. This is 5. And then this is 2. All right. Now what happens? Now look at this. When I have a 2 over here, I know that technically 2, when 2 comes, this is the first node. From this first node, tell me from A1, in this actual, like, what did I do? Yeah. From this 2, the best case on the right hand side, the minimum was 2. Every number in this part is greater than 2. Yes, greater than equal to 2. So which number should you have taken? You should have taken this node only, no? You should have taken this node, 2 node, by this logic we just proved. Yes, this logic. Agreed? So how do I incorporate that implementation? I'll say, all right, now the values.size is greater than 1. And the top value, that is 5 value, that's the top value. It is greater than 2. That is the current value, AI. So let me try to pop them. I will say I will extract the value stop, that is V1, and I'll pop this out. So I pop V1 from, I pop this, like this 5 from this. I'll pop this out. Now, when I have popped this out, I store this value V1. Why did I do that? I will take this value V1 and I'll try to compare this value V1 with the next top. If let's say the next top is like, if this current value V1 is greater than the next top, still greater than equal to the next top, that means this node has to be removed overall. So I will also remove this node 2. Are you guys getting this? And if let's say, like if I would have, when would I have gone in the else part? If V1 would have been less than values.top. So that would have meant, let's say this value, like this value was, let's say maybe 6 and this was 5. Now the new value which came was 2, right? And you had kept the node 2 over here. So now tell me, if you now want to pop 5, can you do that? You should not pop 5, right? Agreed? Yes. So you would have kept this 6 because this 6 would have been a barrier for you to actually check whether 5 should have been kept or not. So in that case, I would have pushed back again V1 in the values and I would have broken. This is the approach. Now by this, what I have made sure is I finally, like now what I'll do is I'll print the stack for you. All right. So I've created a copy and I've printed this stack in an array and I'll show you what is happening. All right. So let's talk about this part. Can you look at over here? This is the first stack of values. This is the second stack of values. Look at the first stack. After 2, I have maintained a monotonic increasing structure. Yes, I went to the next 2, next 3. And that was the best feasible case by the proving I did over here. Look at this part. From 3, if the next possible case was to go only lower, you went to 2 and then you went to 1. Agreed? You directly did not jump from 3 to 1 because you know you wanted to take the leftmost case. So you jump from 3 to 2 and then to 1. Let's say I talk about this case. In this case, tell me, like, if you're standing at 7, which value should you next jump to? Out of all these possible values, the best possible value is 7. So I jump to 7. Let's say this was not 7. This was, let's say, 9. What should have happened then? I jumped from 7 to the next best possible value, that's 8. Then the next to 8 is not 9 and 10 or 9. Direct, it's 8 again. And then 9. Because now from this 8, again, the sub problem becomes like easier because like just I told you, like if you're able to calculate answer for A1, you can keep on calculating your next sub problem answer. Are you guys getting the approach? I mean, the point is implementation is something, it struck me in this part. It can be implemented in any format, right? The idea is somehow or the other, you're able to figure out that how do you remove the useless edges. Now, by doing this, I was able to make sure that I don't encounter more than n edges. Yes, do you agree? Like I cannot encounter more than n edges. Like what can happen is either cases, you had all the edges and the values were increasing. So like 1, 2, 3, 4, 5. In this case, you will have all the n edges connected. Yes, 1 to 2, 0 to 1, 1 to 2, 2 to 3, 3 to 4. This is the jump I would have done. And now I have stored this jump in the stack itself. So when I am stored the jump in the stack, now if I want to calculate the answer is going to be very simple to calculate. What I can do is simply reverse track and get the answer. I will track the last value, that's value.top, pop it out. And the last J node, that's nodes.top and pop it out. Now till values is not empty, cost will increase by maximum of last value, comma values.top into whatever is the absolute difference. Absolute difference obviously will be J minus nodes.top. And then last will get updated to values of top, values gets popped, J gets updated to nodes.top and nodes get popped. And then you can simply print out the cost. All right. I think you guys are now getting the idea, right? Are you guys getting the idea? All right. I think it's clear. All right. So now again, I'm repeating this for anyone who watches the problem later on. Implementation can be done in any format. Proving should be clear. All right. How do you build the intuition that useless edges have to be removed? That's the important part in this. So I am telling right here only that this problem could have been solved by running a Dijkstra by creating the agency matrix of n edges. That can also be done. It has also been done by 2 monotonic stacks. One can be you start off from the beginning and go till the end, or and you also start from the end and go back to the back. So that's also one approach. All right. I just compiled down everything to one monotonic stack. All right, so it's much shorter that way. But then if this doesn't strike you and want to expand that approach, that's not an issue. But the crude idea will remain same. That why did you take the edges in first place in in a greedy manner is because of this proving. All right. So I think this is clear now. Now, can we discuss the time complexity? What do you think is the time complexity? Tell me. Like I have, like for time complexity, can you say that I am running a loop over here, 0 to n? Yes. And then the maximum time I'm actually popping, like for every value that goes inside, it can either pop or it can either push. For every value AI or every value I, whatever you count, because both are done simultaneously, each value either is pushed or popped. Agreed? So can I say that I will have a total, like this total complexity of this for loop will be 2 into n? Or this whole structure will be 2 into n? Because I have n elements and every element is either getting popped or pushed. So for n elements, 2 options, 2 into n. Clear? Again, and because 2 into n can be like written in an order of n, you can write that this overall complexity is n. Do you get this? I think this is clear. Now, because the complexity of this part is n, now if I talk about this part, this is directly n. This doesn't even need some explanation because I know that values size is going to be maximum n nodes, which I just showed you. So this while loop will run maximum n times. So overall time complexity can be reported, like overall time complexity can be reported as O of n plus n, which is exactly 2 into n, or you can say that as order of n. And now what about space? Anything about space? For space complexity, it obviously makes sense for me to take a space, like I'm obviously taking stacks. They can have a maximum size of n. So I can say my space is in O of n order. Agreed? Are you guys clear on this? Can I move on? I think we've done a lot of discussion in this part. Clear? Hello. Is my video audio not lagging, right? Already, yes, clear. Cool. So let us move on to the final problem. All right. Now, this is going to be an interesting problem. All right. Now, the final problem is going to be an interesting problem. Reason being that, like, if I tell you what the idea looks like, and if I tell you that it's out there on the internet, you could have just done this problem in the contest itself. All right. Let us try to look at that. All right. Limit of max. Yep. Now, for an array B consisting of non-negative integers, they have defined something called as the function g, that is b comma x. Now, this denotes that the maximum max of an array B we can obtain, like it's going to give you the value denoting the maximum possible max of a array B, which we can obtain by appending x integers to B. Now, is this statement clear? Does anyone have any doubt to this? Do you all know what is a max? It's written over here. Max is the minimum excluded element, the minimum non-negative integer that does not appear in the array. So let's say that I'm talking about the max of 2014, and this 3 doesn't appear. So 3 is the max. Yes? Agreed? Now, it is written that they have defined a function like this. So the array B is given, and then you have some power to append x integers. So we'll talk about this. 1, 2, 4. In this array, the current max of this array, tell me, what is the current max of this array? 1, 2, 4. 0. The current max of this array is 0. The smallest non-negative integer that's not there in 1, 2, 4 is 0. So the max of 1, 2, 4 is 0. Yes? How do I get to know the max number of a segment? Because would be max plus 1 minus number of unique element. Correct, exactly. That's not in the subsequence, Harsh, in the sub array. I think this is what you must have missed, if I'm not wrong. Yes, all right. I'll be coming to that. All right. So tell me, like, very quickly, 1, 2, 4 has a max 0. Yes. And you have an option to increment the max of 1 to 4. Now, if the max of 1, 2, and 4 is 0, current max is 0, then if I want to increment the max, should I not place this number 0 in this array? If I place this number 0 in the array, I know max is going to be something greater than 0 now. So this is the idea. This is the idea. Meaning, if let's say you have some numbers, A1, A2, A3, A4, so on till AN. Let's say you have these many numbers with you. Then if their current max is M, then you should actually add this M in this array to make a max greater than M. Make the max go greater than M. Do we agree to this part? Yes. So that is the idea behind the problem. That means in a segment, if I'm talking about in a sub array, if there is a sub array with me, and in that sub array, I want to calculate that what would happen eventually. Something like this would happen, that I will keep the current max M in the array itself, and then that max will become something greater. Now, what they have given in the problem is, according to them, there exists a non-negative integer C such that function b comma x plus 1 minus function b comma x is equal to 1 for all x greater than equal to C. So that means after a point of time, what will happen is, whatever number of consecutive x values you give, let's say you talk about g of b comma 5 minus g of b comma 4. This is also going to be 1. Then g of b comma 6 minus g of b comma 5. This is going to be 1. And so on, so on, so on. So after a point, it's all going to be 1. And that point is going to be the value c. So in this case, this is the value c. Because after 4 being x, all the next consecutive x numbers, if are placed in this function, you get a difference 1. Agreed? Yes. So now how do I picturize this c number? It's very obvious. Let's look at the case. I have 1, 2, 4. Now in this, tell me, what is the maximum number? 4. And from 4, what is the number that is missing from 0 to 4? 0 is missing definitely, and 3 is missing definitely. So if I give you the option to add on one integer, you would have said, I will add on 1. Sorry, I will add on 0 to this array. So this becomes 0, 1, 2, 4. And now the max is 3. Next time when the max would have shifted to 3, you would have said, if you would have given me the power to add 2 numbers, then I would have added 0 to make the max 3. Then I would have added 3 to make the max go 5. Now, when the max becomes 5, after this, if I give you the option for 3 numbers, the max will become 6. 4 numbers, you will say max will become 7. 5 numbers, you will say max will become 8, and so on, so on, so on. Agreed? Yes. So don't you think that the point of place where this c value is existing is actually the point where I can say that whatever is the maximum, like these were the initial numbers, I'll mark them. 1, 2, and 4 were the initial numbers. So whatever is the maximum in an array minus whatever is the unique count of elements in that array plus 1. This is my answer for this subarray. So in this subarray, I can see that the unique count was 3. Maximum number was 4. 4 minus 3 plus 1 would have given me 2, which would have meant that 2 numbers, 0 and 3 were missing. After 2 or greater than equal to 2 numbers, if x was given me greater than equal to 2, after that, I know that the maxes would have turned out in a difference of consecutive ones. I can see that very clearly. Yes, but up till 2, I'm not sure. After 2, I know for sure that that would have been the case, that I get the maxes to be consecutive, maximum max to be consecutive. So I know that is going to give me 1 as the difference. So this is the C. Now we have identified the C for a subarray. Are we clear up till here? Are you guys following up till here? Yes? I think there's no problem up till here. All right. All right. Let's move on. Now, the question is actually asking me to do this for all the subarrays and add on. So I want the sum of all possible subarrays after I calculate this C. Yes. So I'll try to boil down this equation. I have 2 summations over here. All right. So those you get the mathematics very clearly. Like this is the summation symbol, right? They have 2 summations. And in these 2 summations, what they're essentially trying to, they have written this function as f of a of l comma r. Essentially what this function means, like what is this function? This is the array a to l to r. If I remove this, I'll write this in my analogy. This analogy is find whatever is the maximum in the array a to l to r, sorry, l to r, minus remove whatever is the number of unique elements in the array L to R, and then add on 1. Is this what we are writing? Now by the rules, like this is mathematics. So like if you understand basic mathematics, you will easily see that this summation, these 2 summations, the constant term in this is 1. Yes, this is the constant term 1. So what you can do is you can say, I will take out this 1. And I will apply summation to this. So that means if I take out this 1 and apply summation to this, what will happen? I will simply be adding the number of subarrays of the whole area, whole 1 to n. Yes, that many number of times 1 will come. Agreed? So how many times that is going to be? Like 1 is going to appear how many times? N into n plus 1 by 2. So this is one part of my answer. That is definitely getting added. Yes. Now, next part. Next part is, this is P1, this is part 1. Next part, P2, is you somehow are able to calculate the summation of, sum of max of all subarrays. And you're somehow able to calculate the part P3, that is sum of unique count of all subarrays. Now, if you're able to calculate, like P1 is directly calculated. If you know N, you can calculate this. If you're able to calculate P2 and P3, then can you simply write the equation as P1 plus P2 minus P3? This is the answer. Do we get this part? Yes. Are we clear on this? So this is the whole idea behind the problem. All right. Now the argument stands over here is like, I don't want to do this typically, but then it's going to extend the PCD to a very large margin, and it's already, I think, 2 hours plus. This problem is a very standard problem in itself. Sum of max of all subarrays. And then this problem is also a very standard problem in itself. Sum of unique count of all subarrays. So even if you open the editorial for this problem, you will find that this thing is something they have done very rudimentally and very easily. All right. So what I'll do is I'll try to give you a very basic idea over this, and then I'll show you a code part on how I have done this. All right. If you get the idea, then it's fine. Otherwise, I do want that this becomes an upsolving for you, because this problem and this problem is a problem in itself. It's like a level 1, level 2 problem in itself. So I don't want to discuss 2 more problems for this problem's sake, right? The part of the idea of PCD is to give you an idea of what I want to do. And I'm arguing this, I can argue this for guarantee that if you search this directly on Google or this on Google, you will get a very good article on this with a very good editorial. All right. All right. So I'm not trying to drop anything. I'm just trying to give you a picture of how this subproblem is going to look like. All right. Good enough. All right. So I'll give you a very brief idea of what can be done in this case. All right. So I'll talk about first thing first. All right. Very quickly. First thing is you calculate you want to calculate the sum of maximums of all the subarrays. And you want to do this obviously faster than an n square solution. Yes. Because n square, you want n square, you will definitely be able to do this. Yes. You can run 2 loops and you will get the part. But then you don't want that. So what you can argue, I can look at each number AI and I can ask myself, this AI value is going to be in how many subarrays is this AI value going to be the maximum? So what I'll do, I have, let's say, somewhere in the middle, this is the index I and this is AI. All right. Now, if this is AI, what I'll find on the left-hand side, if I want AI to be the maximum value, if I move on to the left part, go on to the left part, I will be able to cover a area of segment, after which, if let's say I find a value, let's say I'll call this value AL. If this AL value is greater than AI, then will any subarray that contains AL and AI, will AI be maximum? If AL is greater than AI, will AI be maximum anymore? No. So that means what I can do is, if I want to see the contribution of AI, I will find the leftmost place where I see that there was just next to it, there was a value AL, which would have given me a value that's greater than AI. So I can stop over here because I know that now after this AI is never going to be the maximum. Agreed? And then on the right part, what I'm going to do the same thing for a value, let's say AR. One difference is going to be AL is going to be greater than AI and AR is going to be greater than equal to AI. So essentially what I'll try to do is, on the left part, I'll be finding the leftmost larger element, and on the right part, I'll be finding the next best, next greater element, next greater equal element. All right. Now, if I find a next greater equal element, I have covered a segment. This is the segment. I have marked this segment. Now, in this segment, I have the possibility to choose any index as I and any index as j and create a subarray out of this, making sure that AI always comes. So I'm sorry, let me not take this as AI. Let's take this as LNR. All right. If I take, no, not LNR also, some new variables. Let's say X and Y. Yeah. If I keep any index X in this area, any index Y in this area, then combination of X and Y, the subarray will always contain AI and AI will be the maximum. Yes, so we'll multiply with number of area. Correct, exactly. So what will happen is, if I have found this index, like if I know that this is the index, that it's the largest index less than I, where the value is greater than AI, and then I found this index on the right part, let's call this index Ri and let's call this index Li. I have found Ri which is greater than I, and has an element greater than equal to AI. Then AI will be the max of any subarray, I should say any subarray A of L2R, any subarray A of L2R, such that Li lies in X, lies over here as Y, and is less than Ri. Do you agree? Yes, any X that lies in this range, greater than Li but less than I, and any Y that lies in this range, greater than equal to I but less than Ri, it is going to give me the possibilities to select X and Y. Now, if this is the case, how many subarrays should be there? This area multiplied by this area. That is the combination I can take for X and Y. Agreed? Yes. So if I write this in this terms, what will that be? It will be I minus Li into Ri minus I. Yes. This is going to be the number of subarrays where AI is maximum. Now I want AI's contribution. So I will multiply this with AI again. And this is the number, this is the count, sorry, this is the number of subarrays where AI would have been the maximum. So this is the number of times, I will multiply AI and add this to my answer. Are you guys following up till here? Now to implement this, how can I do this? Can you not think of a stack approach? We know monotonic stack. So indirectly, when I say I'm starting at an index I, I'm trying to find the best next largest element on the right part and also on the left part. So it's kind of a stack solution. Yes. So you can do this with monotonic stack, or maybe you can create prefix and suffix, something like that, or maybe you can do some better approach. Somehow or the other, if you search this question, sum of max of all subarrays on Google, you will find a very clear approach on that. And this is what they will be doing essentially. Like they will be calculating this part, but then we don't want this part. We don't want the number of subarrays. We also want the number of subarrays into AI because we want the contribution. So we'll multiply with AI again. Agreed? Can you all agree to this? Yes. Okay. Understood. Cool. So this part is clear. Now I'll move on to the next part. Now, if you calculate the max is done. How do I calculate the unique thing? Now it is again kind of the same thing. We focused all our energy on AI and we said, how many times did AI contribute to a subarray to become its maximum? We are going to do the same logic over here also. In this, what we'll do, we will fix a value X. All right. We'll fix some integer X and we will ask ourselves that we are going to count the number of subarrays that contain at least one occurrence of X. So if I'm able to calculate the number of subarrays where there is at least one occurrence of X, that means over there, X will contribute 1 to my answer as uniqueness. Do you get this part? I mean, this can be confusing a bit, but do you get this logic? Like I'll try to repeat this part also. Like, let's say you have the numbers 4, 3, 5, and 4 again. So this number 4, in all the subarrays where there is at least one occurrence of 4, this 4 will add up as a uniqueness part. So if I talk about the subarray, like if I talk about this subarray, it will add answer 1. This subarray, answer 1. If this subarray, answer 1. And in this subarray, again answer 1. Because 4 comes 2 times, but contribution is done only by 1. 1, 4. Because I know 4 is repeating, but I want unique part. So what I can do is I can fix a x value and I can ask myself that where do I think this x is going to contribute 1 as an answer? So to calculate this, what I'll do a reverse approach. Tell me, what are the total number of subarrays? N into n plus 1 by 2. Yes. From this total number of subarrays, if I want to calculate the number of subarrays where there is at least one occurrence of x, which means what I can do is from the total subarrays TSA, I can subtract all the subarrays where there is no occurrence of x. No occurrence of x. Agreed? Can I do this? So now this like you must have done this problem kind of in probability. Like we do kind of like this solutions in probability, right? If we have a total, like if you want to calculate some part of the search space, we can do that by taking the whole search space minus whatever is the bad search space. That is going to give us the good solution. So this is something we can do over here also. So now I have the total number of subarrays n into n plus 1 by 2. If I want to calculate all the subarray counts where there is nowhere x is coming, how can I do that? Very simple. Let's say in the subarray, let's say in the main array, let's say x came over here, x came over here, and let's say x came over here. So all the part, this part, this part, this part, all these 4 segments where x was not there, any subarray that is getting formed in this part itself will give me the answer. So let's say the length of this part is d. Then d into d plus 1 by 2 is the number of count of subarrays that where never x will occur. Similarly, if let's say this is d1, let's say the size of this segment is d2, then d2 into d2 plus 1 by 2 is going to give me the number of subarrays where never x will occur. Similarly, this will be for d3, this will be for d4. Agreed? Yes. And when I sum everything up, I can actually minus that out from this part. Now, do you get the idea? Yes. So this is what can be done. I can like now. So in this part, what you can do is for every possible value of AI, you can store the indexes where it gets saved. Let's say I stored this index I1, I2, I3, and so on. And then you can find the segments. And then you can deduce the length of that segment and subtract that from the whole part. Now, is this clear? Now, again, if you search this problem on Google, you will find a very straightforward solution doing this, what I've told you. So that is why this is a sub problem. And that is why I'm not going to go in the proof and the whole part of why this is happening, show you the implementation, try to prove you the implementation. You can just understand this within any good article out there and you will get the implementation directly. All right. So now can I move on to the implementation part? I think I should. All right. All right. Cool enough. All right. So now taken the array input, taken the vector input, created 2 stacks because I wanted monotonic stack structure. Next greatest, previous greatest. This first I find the next greatest. How do I do that? By iterating obviously from n-1. Now this is very straightforward monotonic stack creation. I'll check is array of top less than equal to array of I because I know I wanted the array AR elements greater than equal to. So this is what I've done over here. Now if I do the same from 0 and keep a check less than AR, this is going to give me the AL values. And this would be previous greater. Pushed in the both stacks, ST1 and ST2. Is this clear? Using the stacks ST1 and ST2 with the next greater and the previous greater element. Now this is a prerequisite. Monotonic stacks should be known in this. All right. Now once this is done, once you're able to figure this out, you can calculate the contribution of the max part first. So I want to calculate the contribution of max part. How do I do that? Taking the answer, left part. What is the left part? I minus PGI of I. This is what I told you, right? I minus Li into Ri minus I, that's the next greatest, Ngi minus I. That's the right part. Multiply both and multiply with its AR, add on to the answer. This is the contribution of array of I. Agreed? Do you agree to this? Yes. Now, my approach to calculate this maximum is kind of a bit different. What I've done is I have created a map. All right, I can even take this as unordered map. It's going to work fine, I think. I've created a map where I'll store the last occurrence of every number. To get this, like instead of doing this vector, like I could have created a vector for AI number, stored A1, I1, I2, I3, so on. But what I've done is I have maintained only a map structure to actually get this part. So first, everything will be -1 because nothing has occurred first. If something occurs first, then this is the last occurrence of I1. I am standing at I2. I will calculate the difference. This is what I've done. So I'll go to this part. I'll say left part is like, first I'll calculate the total subarray segment between this. That's I minus PGI, and this is NGI minus I, same as the above. Then the count is 0. Then what I'll do is I'll update my, like this, I have done this part to calculate the suffix also. So like you also want a segment that looks like this, right? After I3, you also want a segment. So I've done that part. And then what I've done is I have added on to the count to that answer, right into left. This is the total number of subarrays. Now, if there is no occurrence of array of I, that is in the last, if the map, in the map it doesn't occur, that means I'll initialize that value to be -1. That means it's the first time it came. So the left part would be PGI minus last of array of I. And then I can remove that number, like how many number of times will it come? N minus I number of times. So I'll add this to the count. Now this is the overall like number of, I should say, occurrences where X was not occurring. I will deduce this from the answer. So this is the subtraction contribution. Again, implementation is not a part, right? Like how I told you over here, you can do that way also. You can take two indices as pairs and you can do that. You can maintain a map. You can do, like, it's not going to bother you if you get the idea. Agreed? All right. So, I mean, I have just like taken up, and I'll give you very straightforward, like this approach, like this sort of an approach is directly out there. So I have taken some part of that out there also, right? So that's the whole idea, because sub problem was something that's out there. So most of you or most of them would have actually taken up this directly. This is something you don't have to run your mind into, but we should have understood that what this sub array structure, like what this equation should have boiled down to. All right. Cool enough. Now this is what I've done. And once that is done and dusted, you can print your answer. All right. So I think it runs on this case, and I think it should run otherwise also. Yep, runs. So now what is the time complexity? Now to calculate the monotonic stack structure, time complexity is actually in order of O of n. Like this is monotonic stack creation. Next greater, previous greater, you can just Google that up. You will get an O of n solution. And this is also O of n solution for the next monotonic stack. Now over here, the contribution, this is also O of n. Yes, I have an O of n structure over here also because I have a 0 to n loop. And the same for this part. Yes, I have an unordered map. So because of an unordered map, I have all the time complexities running an average of constant. So this also has a O of n structure. Yes, this also has a O of n structure. So overall, can you tell me the time complexity now? Very clearly, the time complexity is O of n. Yes. And what about space? I'm using some stacks, and like can say like I'm using 2 stacks and some vectors also, all of size n. So overall order can still be reported in O of n. That's for the space part. Is this clear now? Now I'll be uploading the codes very cleanly and very neatly. So for everyone who has watched the video up till here, you can check out the codes in the description and you will get the clean codes. All right. This was just done in a haphazard manner for the video, but then the idea should be clear. Like I have tried to keep up very slow with all the process. So if, all right. Yeah, I'm doing an internship there. Yep, Harsh. All right. So I think I am good to go in this part. I don't think we have any doubts. And yeah, this is a good place to stop. So thank you, everyone. Let me stop the recording.